This is the periodic table. Noble gas are stable. Halogens and alkali react aggressively. Today, we're going to be talking about the one and only, the periodic table, your chemistry soul. And hopefully by the end of this video, you should be able to explain why the periodic table is organized in the manner that it is. For today's timeline, we're looking at first going over a lot of the periodic table verbiage, a lot of the words and terms that we use to describe it, and the groups that it's organized into. So that includes a lot of these period level, family names, the characteristics, atomic size, electronegativity, ionization energy, Coulomb's law, and reactivity, just to name a few. We're also going to be explaining for each of those categories what they are and why they matter. So that's pretty much the summary of today's lesson. Let's jump right in. If you're curious to hear the rest of that periodic table song that I started the video with, please feel free to click on the link in the description below to find this video here. It's excellent, love this video, great periodic table song, and sings every single one of them all the way through. Highly recommend. Definitely go check it out. But for right now, we're going to jump right in with our organizational terms for the periodic table. So we've got our little Stitch friend right here, and he's so cute. Look at him, he's all stubborn and he's all upset and whatnot. But he's there because he's representing a group or a family. So just like Stitch would say, a hammer means family, and family means nobody gets left behind or forgotten. So that's kind of also what we're looking at in the periodic table. These are directional terms. So we're talking about which way we're reading it. Are we reading it from left to right or top to bottom? That's kind of what we're using these words for. So a period or level, that's if you're going from left to right or right to left. So if you're going across the periodic table this way, then you're talking about a period or level. An easy way to remember that is that, ladies out there, if you get your period, you mark it on your calendar, and your calendar goes from left to right, right? So if you're thinking about your period or a level, that would be going from left to right across the periodic table. Sorry, gentlemen, had to throw that at you, lady stuff. But that's a good way to remember it. A group or family, as Stitch would say, would be going up and down. So vertical columns going up and down. So if I'm talking about a family on the periodic table, you should be thinking that it's a vertical orientation. We're thinking about up and down. If I'm talking about a period or level, I'm talking about orientation left to right or right to left. There are less efficient ways to model the periodic table. Of course, this one would be my personal favorite. Maybe not as easy to read, but I mean, it models ducks, so it's, you know, Duckonta. Yeah, okay, you guys get it. All right, so the periodic table organization, the other way we organize it is not only from left to right, top to bottom, but we've also got the periodic table subdivided into larger groups known as metals, nonmetals, and metalloids. So metals are the things that conduct electricity. Those are things that, you know, are shocking, so to speak. A nonmetal does not conduct electricity. A metalloid, sorta, it's like wishy-washy. It wants to conduct, maybe sometimes it acts like a metal, other times it doesn't. It's a metalloid, it's metal-ish, if you will. And those are along the staircase. So if we're looking at this periodic table over here, you can see that the metals on the periodic table are everything in blue. So all the blue over here, those are all metals, things that conduct electricity. Things like disturbed, right? Conducts electricity. Metal, right? So we've got a whole bunch of metals that are blue on that side of the periodic table. Now, there are also things that don't conduct electricity. For example, like Miley Cyrus. I came in like a wrecking ball. She's not electrocuting anything. It's more like, ugh. Okay, anyways, personal opinion here. We can all differ on our opinions. It's fine, right? Okay, so Nonmetals would be the stuff in green over here, and that would be the stuff that's nonmetals, does not conduct electricity. Again, metalloids are right here in that staircase or that stair step, because it kind of looks like it. It goes and separates between the nonmetals and the metals. So it's that dividing barrier between the two, symbolized here in orange. So some special metallic properties we want to consider. This would be for all the blue stuff, again, the metals. So we're not looking at green or orange right now, we're looking at the blue stuff. So these are some cool properties of metals. Some metalloids can sort of do this, so some of the orange ones can sort of do this. Again, they're metal-ish, so that's why they're metalloids. They conduct electricity. That means that electrons can flow through them. That means you can get zapped. Really fun story about electrical conductivity in my personal life. When we still lived in Arizona and we were renovating our kitchen, we had one of those hood things that just collects all the steam from when you're cooking over the oven. We wanted to put a microwave over our oven. So me, being a chemist and not an electrician, I will throw that out there, disclaimer, decided to remove that little hood thingy to get ready for the microwave. And I was holding one side of the wire, and we didn't turn off the electricity to the house or anything. We didn't turn off the breaker. And, I saw the other side of the wire, and I was like, oh, I need to move that. And so I was still holding on to the one side, and I grabbed the other side, and probably for a solid, 20 seconds, I want to say, I was standing there doing this, holding on to both ends of this wire. I had basically completed the circuit, and I was getting electrocuted. Probably not a great thing. I would not recommend. Definitely would not recommend. But electrical conductivity is what allows those electrons to flow through metals, flow through wires. Wires are metal. Thermal conductivity is when you have heat flow through a metal. So if you've ever cooked with one of those really ancient pot things that don't have a nice little silicone handle or anything to protect your hand from getting scalded, you know personally that if you put that pot on the stovetop and you let it sit there on high for even just 5-10 minutes, and you go to grab the handle, you're going to be regretting it. You're going to be like, ow, that really hurts. That's thermal conductivity. We also have malleability. So malleability is the ability to form metals into shapes. This is something that most metals can do fairly easily or well. So if you're thinking about swordsmithing or anything like that, like the picture shows there, then you can see that their swordsmithing is actually a useful thing in our history. We use that to make swords, we use that to make all kinds of tools, doorknobs, door handles, all that kind of stuff. Ductility would be that you can make it into wires. So basically you can take a metal and kind of thin it out and coil it into wires, which is also very, very useful in terms of our electrical age, everything that we use wires for. So again, above my head, that would be electrical conductivity. That's what makes putting a fork in the outlet oh so dangerous, because then you're allowing the electrons to flow from said outlet into your body through the fork, through that metal. Also, the swordsmithing for malleability. Let's give it a try then. I would love it if you would pause the video here and try it yourself. See if you can identify these different chemicals, these different elements on the periodic table, and tell me, are they metal, nonmetal, or metalloid? Let's try it ourselves. If you haven't paused, you just want to know the answer. Well, first and foremost, if we're looking for aluminium, that is technically the correct way you're supposed to say it, by the way, is aluminium. If we're looking for aluminium, that would be Al. Al is right here, and it is on the blue side. That would be a metal. So aluminium has the properties we just talked about. Could have electrical conductivity, could have malleability, could have thermal conductivity, all of those things that, think about tinfoil, right? If you put it in the oven, it gets hot, but it actually cools down pretty quickly. So thermal conductivity. If you have aluminum foil and you try and wrap it around your sandwich, it has malleability. You can shape it how you want to shape it. Cool. Silver. Silver is Ag. That's right here. Silva. So silver is also blue. So that would also be a metal. So the thing that makes up your jewelry pieces, your rings, your necklaces, your silverware, right? That is something that also conducts electricity, thermal conductivity, potentially ductility if you were going to use it for wires. Let's find yttrium. Yttrium. That's the Y right here. And Y is also blue, so it is a metal, has all those properties we just talked about. How about tin? Tin's symbol is SN. SN is right here. SN is in the blue area, so it is also a metal. How about selenium? Selenium is Se right here. That's in the green, so that means it's a nonmetal. That means it does not conduct electrical conductivity. That means it does not have thermal conductivity. That means selenium is not malleable. So those are all the kind of things you want to think about. The green is everything that the blue is not, essentially, for the most part. Let's take a look for nitrogen. That's N. Nitrogen right here. Nitrogen is also green. That makes it a non-metal. It has none of the properties we just talked about, for the most part. Astatine. Astatine. Where is astatine? Is right there. AT. That's also in the green. That's a non-metal. All right. So how about, let's say, silicon? If we were looking for silicon, that would be Si. Si is right here. And since that's in the orange range, that would be an example of a metalloid, something that's metal-ish. It's kind of on the stair step between a non-metal and a metal. All right. So now that we know about levels, periods, right? So going across, and we also know about groups or families is going up and down. Then we need to know what the names are for those families. So just like in your family, you have a family name, you have a last name that you carry on through your heritage. There's also family names for the periodic table, and these are our group names. So the first family name that we're going to look at is called the alkali metals. So everything going up and down in this vertical column is an alkali metal. They share very similar properties, being that they are in this same column together, but we'll get there. The important thing to know is that all of them in this column are called alkali metals. Now in the column adjacent to it, those are called alkaline earth metals. Alkaline earth metals. All of these metals in the middle over here, notice that these are both metals. They were both on the blue side. They're still metals. All of these here in the middle are known as transition metals. Transition metals. Then down here, we're looking at inner transition metals. So if we go back, you can kind of see that on the periodic table, there's a little star and a hashtag, a number sign. So hashtag for all of you youngins out there. We've got a star and a number sign, and that means that technically these two levels right here are supposed to be squeezed in right there. So technically the periodic table is squished like this, the way you're looking at it right now. But really, if these were inserted up here, the periodic table would be really long, because you'd be squeezing these right in the middle with nothing on top. And that's not visually appealing, so we usually just keep it down there. And we say technically they belong right there. So those are called inner transition metals. Transition metals and inner transition metals. On the far right of the periodic table, we have the halogen group. The halogen group, or the family name of halogens. We also have our noble gases. Noble gases in that far, far right column, going up and down. This stair step that I mentioned, remember, that is what is separating our nonmetals from our metals on this side. And that stair step, and along that stair step, we have the metalloids on either side. So then what are some family characteristics of these different families we've just been talking about, these different groups? Let's go through each one by one. So first and foremost, the noble gases, they're kind of snobby. They're like noble, right? And we have full outer shells and we're stable. We don't need anybody in our life. So the noble gases don't really mingle or react with other chemicals because they have everything that they need already. They don't really need to react with anybody else. They're just chill, being who they are. They're noble. The halogens, though, right next to the noble gases, are pretty reactive. They're very reactive, in fact. And their name technically means salt producing, because when halogens react with other metals, so remember the halogens are on the nonmetal side, but when these halogen nonmetals react with metals, they produce a wide range of salts. There's more than just one kind of salt. There's more than just table salt. There's hundreds of kinds of salts. We also have the alkali metals. This was on the far left side of the periodic table, and they are all shiny, soft, and highly reactive metals. These are, again, on the metal side, hence why we call them alkali metals. And we also have the alkaline earth metals. They are silver colored and also soft. Now, when I say soft, I'm implying not like when you pick up a nickel and you can clunk a nickel on a table and it goes thud, thud, thud. When I'm saying soft, I mean you can literally take this metal with a plastic knife and slice off a piece of the metal. You can just slice it right off like cheese. That's what I mean by soft. They have relatively low densities, melting points, and boiling points for the alkaline earth metals, meaning that lower density means that it's likely to float on water if it has a lower density. If it has a low melting point, it means it doesn't require a lot of energy in order to get it to melt. And boiling points, meaning again, it doesn't require a lot of energy to get it to boil. Transition metals, and also including those inner transition metals here, have the ability to transition their charge. They literally don't have to stay the same charge all the time. They can kind of morph to the situation they're placed in order to best accommodate a reaction or best accommodate the stability of two chemicals coming together to share electrons and make a bond. They are transitioning depending on the circumstance. All of the other guys, they're pretty much dead set on the charge they can be. The transition metals, however, can change charge depending on the situation, which is pretty cool. Some observable trends. If we're going to go down a group or down a family, what we can see then is that the atomic radius will always increase. In other words, an atom will get bigger and bigger and bigger as you go down a group. So in this case, if we're looking at this arrow here, which one of these atoms would be the biggest? Which one would be like the kahuna atom? Hopefully you're thinking, okay, well, if it gets bigger as we go down, then francium would have to be the biggest atom. It would have to be pretty big. And you would be right, because the size increases as you go down. So francium is the lowest point, and it's the biggest atom. If we go across a period or across a level, what we see is that the atomic radius will always decrease. In other words, you get a smaller and smaller and smaller and smaller and smaller atom, meaning the electrons aren't spread out as far around the nucleus. So it's tighter knit electron cloud. The atomic radius will get smaller as you go from left to right across the periodic table. So then I would ask you, what is the smallest atom given that? So given what I just told you, that if you go from left to right across a period or across a level, you should have the smallest atom. That would mean from going from left to right, that helium would logically be the smallest atom, and you would be correct. That is the tiniest little tiny guy we have on the periodic table. So then we have this trend. We have this trend where an atomic radius being defined as from the nucleus to the outermost electron. So when we're talking about that atomic cloud, right, where all of the electrons are floating around, and we know that it's not planetary, we know that they're kind of just as this density floating around the nucleus. So the farther away they are, that radius from the center of the circle, so the center of the atom, the nucleus, to the outermost electron where it's likely to be, the probability of finding one there. That's going to be your atomic radius. We have an overall trend if we're looking at the whole periodic table then. Remember, we said that going down we get bigger and going across we get smaller. So overall, if we have an arrow that's kind of drawn like a hypotenuse through the middle of our periodic table, what we see is we go from smaller radius from the top right-hand corner to larger radius at the bottom left-hand corner. This is a really important trend that you should memorize and that you should include on your own periodic table at home if you have one. So again, bigger atoms are always going to be in that bottom left-hand side. Smaller atoms with a smaller radius are going to be in the upper right-hand side. Now, I mentioned charges before. These charges are based on the outermost shell. This is called the valence shell. This valence shell has a certain number of electrons, and those electrons correlate to the charge that an atom can form. So in other words, if we were going to look at our first family, our alkali metals, and we were going to look at lithium. Lithium is an alkali metal. Notice that in the outermost shell, in the valence shell of lithium, there is only one dot. There is one electron. Notice that where lithium would be over here on the periodic table, it's +1. That's because in order for lithium to have a full valence shell, a shell that makes it stable, like the noble gases, it could lose this one electron. It would be pretty easy to just kick out an electron, lose one, and if you lose an electron which is negatively charged, then it becomes positively charged, right? So if an electron, X-nay, you're out of here, then this means that lithium overall becomes a +1 charge. Now, all of the alkali metals in this family have that same ability. They all have just one little measly electron in their outermost valence shell. And it's easy for them to lose that one in order to become a +1 charge overall. Let's move over to our alkaline earth metal group. Let's pick on calcium. Pick on calcium here. So calcium, if you look in its valence shell, the outermost shell, so we don't care about all the stuff in the middle, all the gobbledygook, just the outermost shell. We'll see that we have 1, 2 electrons. So in calcium's world, and also in all of the other alkaline earth metals worlds, it's easier for them to lose these 2 electrons than to gain an extra 6 in order to have a full shell. The reason that they would gain an extra 6 is because every single atom wants to be like the noble gases and have an octet, have 8 electrons in the outer shell. In order to do that, it's easier just to lose 2 instead of gaining 6, and voila, look, now calcium has 8 in its outermost new shell. That would make it stable like the noble gases. That's why if you lose 2 negative charges, you become +2 charge, just like all of these guys. Now remember, we mentioned that the transition metals and the intertransition metals transition charge. So they don't have a set charge. They don't have a set number of electrons that are in their outermost shell like these guys do with fixed charges. That's what makes them special. They can change their charge depending on the circumstance. Let's jump over to these guys right here, these 2 little +3s. Boron is one of those +3s. Boron, he's so boring. Anyways, boron here has 3 dots in the outermost shell. We've got 3 electrons. So again, it is easier for boron to lose those 3 electrons than gain an extra 5 in order to have 8 in the outermost shell. And that means that if you lose 3 negatives, you become plus 3 overall. Let's jump over to carbon. Carbon is in this red column, this kind of special case, if you will, column. So carbon has 4 electrons in the outermost shell. 1, 2, 3, and 4 down here. So because it has 4, it's halfway to 8. And that's why it's a special case. It could be just as easy to gain 4 as it would be to lose 4. So in this case, carbon's just kind of like, depends on the circumstance what it's going to do. So we can't give it a solid charge based off of that. Nitrogen right here is in this family. We didn't give that family a name. That's okay. Most of the time you don't ever refer to that name anyways. It's not very common. So this guy is where we start going to the negatives. We have -3s. Now the reason for that is because nitrogen has 5 electrons in the outermost shell. 1, 2, 3, 4, and 5. So because it has 5 electrons in the outermost shell, it is easier to gain 3 extra electrons to have 8 outside, thereby making it -3 charge by gaining 3 more negative electron charges. Moving on to oxygen. Love is like oxygen. So we've got this column right here. And again, we did not name that column. That's okay. We don't typically refer to those by name anyhow. But we've got oxygen here. And in oxygen's outermost shell, we have 6 electrons. So all oxygen needs to do is steal 2 electrons from someone else. So gain an additional 2 negatives, 2 charges that are negative, and become overall -2 in order for it to be like a noble gas and be stable. That's the reason why all of these guys in this column are also -2 charged. Last but not least, we've got chlorine. Chlorine right there. And chlorine has 7 electrons in its outermost valence shell. Because it has 7, that means it only has 1 more to go to be like a noble gas. That's also what makes it so reactive. It's right there. It's on the threshold of being noble, and it will do anything to get it. So chlorine is 1 away. All it's got to do is steal 1 electron from someone and become a -1 charge to be stable like the noble gases. So again, the variable charges for the transition metals and intertransition metals are because they don't have this fixed property of the number of valence electrons in the valence shell. They can change depending on the circumstance. Ionization energy. What in the ionization? Ionization energy is the amount of energy needed to remove an electron from an atom. So if you wanted to rip an electron off of an atom, how much energy would that take to do that? That's called ionization energy. So if you have a really big ionization energy, it means that it is really hard to rip off an atom or an electron from that atom. In other words, if you're really, really tiny, it's harder to rip an electron off of you. So think about our atomic radius. When we're talking about the size being smaller, that was up in the right-hand corner, and the smaller you are, the harder it is to rip an electron off of you. That means that if you are small atomic radius, you also have high ionization energy. So this is opposite of the size trend. An ion, by the way, if you are curious as to what ion means, is basically just an element with a charge on it. So everything we've been talking about, all those fixed charges, variable charges, things like that, an ion is something that has a charge on it, a non-neutral atom. So for example, if you lost an electron, then you would become positive, as mentioned before. So you lose something that's negative and you become positive, right? Just like in your real life. If you lose negativity, if you're generally like, sad or if you have any kind of negativity in your life, maybe you're holding a grudge or something like that. If you lose negativity, you tend to become more positive, more cheery. Same idea here. I know it's a little confusing, so try and play with that in your head there between the gaining and losing electrons. Electrons are intrinsically negative, so if you gain them, you become negative. If you lose them, you become positive. All right, so let's go over this atomic radius versus ionization energy trend and compare the two together with a very silly analogy. Which is easier to remove? Would it be easier to rip the arm off of my body? So just like literally, if you were to come into my house and try and rip the arm off my body, would that be pretty hard? With just your own brute strength. You can't use a chainsaw, you can't use axe or something like that. You just have to rip my whole arm off, like one foul swoop. How hard would that be? Probably a little hard, right? I mean, I'm not a bodybuilder, but like it would still be pretty hard to rip the arm off my body. But how hard would it be to rip the arm off of a baby doll's body? So if you had a little baby doll, like the really freaking creepy one that I have the picture of on this slide, if you have that thing that's like literally it looks possessed. I don't know about you guys, but like it's looking into my soul when I look at its eyes. Anyways, so that baby doll, if you were going to try and rip the arm off of its body, it would be a lot easier for you physically to, maybe not emotionally at this point, just based off of how it's like probably putting you under its spell. But it would be physically a lot easier for you to rip the arm off of the baby doll than off of me. That means that I have higher ionization energy than the doll. It is harder to take away my electron than the doll's electron. I have higher ionization energy. Now let's connect that with the atomic radius. If we were going to talk about candy, if I had my gummy fruits here, my candy, and I was going to hold it like this, how easy would it be for you to steal my candy like this? Probably pretty difficult. It would be pretty difficult. You'd probably have to wrestle me for it. And, I'd probably punch you because I love gummies. So don't try and wrestle me for my gummies. But if I had my gummies like this, like right there, you could just reach out and grab them. Yummy gummies, right? You want to just grab them. Just grab them. How easy would it be for you to grab them? Pretty easy, especially if you could reach through the computer, right, and grab them. So if you could come and grab them, you could literally just take them from me right now, as opposed to if I'm clutching to them. So the idea here is that when I'm holding them far away from myself, that's like having a really big atomic radius. The atoms are holding their electrons really far away from their nucleus. It's easier to grab those electrons. However, the atoms that are smaller, they are holding their electrons really, really tight, really close, like clutching to their candy. So it's harder for them to have their electrons stolen. This is the reason why if you have a smaller atomic radius, that you have a higher ionization energy. It is harder to remove that electron from a small atom. In other words, the trend that you need here is that a big atomic radius is equivalent to less ionization energy. So this is a time when size does matter. Yes, bigger atoms means that they are easier to remove electrons, means that you have a small ionization energy. Whereas if you have smaller atoms that have harder to remove electrons, they have a big ionization energy. You require more energy to steal these gummies when I'm clutching to them tightly, as opposed to less energy if the electrons are right there for you to grab. Let's move on to electronegativity. Electronegativity is an atom's ability to attract an electron to itself. So this would be trying to attract an electron from a different atom. Electronegativity has the same exact trend as ionization energy. So electronegative atoms love electrons, hence electronegative, electron negative. They want to be negative. They want to steal electrons. They're greedy for them. So electronegative atoms will increase as you go from the bottom left-hand corner to the top right-hand corner of the periodic table. So the most electronegative element would therefore have to be fluorine. Fluorine, if you can tell here on the periodic table, has an electronegativity value of 4. 4. That's the biggest electronegativity value we can have on the entire periodic table. Notice that although helium was the smallest atomic radius, it is in the group of noble gases, so it's not reactive. It's not going to be greedy for someone else's electrons because it's already snobby and completely content with its life the way it is. So whereas fluorine right here is a part of that halogen family, the halogen group, and it does want to steal someone's electron. It needs to steal just one to be like the noble gases. And so it will do anything to do that. That's its electronegativity. So let's compare now ionization energy and electronegativity, how these two kind of go hand in hand. Kind of going back to the gory analogy of ripping off body parts here, ripping off limbs. If you were going to bump into Arnold Schwarzenegger, by the way, he also is from Austria, which is great. That is also where my family's from, in Austria. So I love Arnold. He's wonderful. So if you were going to try and steal candy from Arnold or rip his arm off, could you do that? No, of course not. You cannot. You cannot rip Arnold's arm off. I'm sorry. If it was already harder to rip mine arm off, you cannot rip Arnold's arm off. Like, it's not going to happen. He has a really high ionization energy. So if we see someone that has really high ionization energy and we stick him with someone like a chihuahua, and we're going to place bets on who's going to win this tug of war. Who do you think would win the tug of war? Obviously Arnold. Obviously. He has really high electronegativity, meaning in this case, the chihuahua would be like an electron from a different atom. And Arnold, being a very, very strong, high ionization energy, meaning that you're not going to rip the electron off of him, but you know what? He's sure going to rip that electron off of you. He's going to win the tug of war of ripping an electron away from another atom, in this case, the chihuahua. You can think of this in terms of a little cartoon here. If fluorine and hydrogen were having a tug of war, fluorine, as we just mentioned, has the highest electronegativity on the periodic table, which means that it also has really high ionization energy, and it's really small. It has a very small atomic radius. Notice that it is fighting with hydrogen. Hydrogen is on the other side of the periodic table, and although it also has a small atomic radius, its electronegativity is not anywhere near fluorine's, and that means that fluorine is more aggressive in stealing the electrons from hydrogen. Hence the reason why hydrogen's like, no, not my electron, and fluorine's like, your electron will be mine, ha ha ha. So fluorine is the bully in this case. You can kind of think of high electronegativity as bullies. They're going to steal electrons from anybody. That brings us now to Coulomb's law. All of these periodic table trends we've been talking about are due to this fact called Coulomb's law. And now Coulomb's law is basically how the proton will pull on the electron charge and distance. So this is that balance between a proton's pull in the nucleus of an atom on an electron somewhere within the electron cloud. And if it has a strong pull, that electron is going to be kept tight towards the nucleus. If the pull isn't as strong, you have more electrons that are kind of floating farther away from the nucleus. This is Coulomb's law. It's a measure of the force of the pull of the protons on the electrons, the positive charge on the negative charge. So when we think about it, it's about radius. It's about how far and how strong is that pull. So if we're thinking about Coulomb's law, it's represented by this equation right here, where force is equivalent to the charges divided by the radius, the atomic radius. So if we have a charge that's really, really big over a radius that's small, you end up with a big number. If you have a charge that's small over a really big radius, you end up with a small number, which would be a small amount of force or a big atomic size. Let's take a look at this. I'm not big on just spouting out numbers and trying to calculate in my head and things like that, so I like to see it. So if electrons are farther away, then what we say is that the r squared in the denominator is a big value. Those electrons will feel less force, less pull from the nucleus because they're farther away. That means that the ionization energy is small and the electronegativity is small. Since the ionization energy is small, it's easier for other atoms to steal the electrons from them. So bigger atoms are easier to steal from. If electrons are closer to the nucleus, then the r squared in the denominator is a small value, and those electrons feel more of a pull from the nucleus to hold on to them tight, to hold on to their candy tightly, right? So then we say that the ionization energy is big and the electronegativity is also big or high. That means that it's really hard to steal the candy from them. And in fact, they're really good at stealing candy from other atoms that have small ionization energies and electronegativities. So the way to visualize this with numbers would be that up here for Coulomb's law, the force would only be 0.02 if the charge was small, like the number 2, and the distance was big. So if there's only a really tiny small charge in the nucleus and the electrons are really, really far away, then that's when you have a small IE and a small EN. If you have a really big charge, a really big pull of protons on electrons, a big number, and a small radius, so holding it tight, and a lot of charge between this distance, holding onto it, then this is a really strong grip on the candy. That's a big IE and a big EN. All right. Last but not least, we have reactivity. I'd like you to kind of see the differences in reactivity. And thanks to the posters of this video, originally this is not my video, but it's a really great representation of the trends that we see for the halogens. So we're thinking about the halogen family for this video, and we're going to see how reactive they are in comparison to each other.
Here are the 4 halogen elements: fluorine, fluorine, bromine, and iodine. Fluorine on the left is almost colorless. Next comes chlorine, which is greenish-yellow. Fluorine and chlorine are both gases at room temperature, but bromine is a liquid, and iodine is a solid. Even so, they're both quite volatile. You can see the colored vapors, orange-red above the liquid bromine and purple above the solid iodine. Whether solid, liquid, or gas, the halogen elements consist of diatomic molecules, F2, Cl2, Br2. A stream of fluorine instantly sets iron wool on fire, and it does the same thing to charcoal. Now let's see the reaction with hydrogen. There's hydrogen in the balloon. A jet of fluorine gas pierces the balloon and explodes with the hydrogen inside. Let's see it again in slow motion. Now you can see the fireball more clearly. Now the reaction between hydrogen and chlorine. I light the hydrogen at the jet and lower it into a jar of chlorine. The hydrogen carries on burning, but with a pale blue flame. When the halogens react with hydrogen, the hydrogen halides are produced. HF, HCl, HBr, and HI. In each compound, chloride. Now let's see how the halogens react with aluminium. When aluminium powder meets fluorine gas, the reaction's over in a flash. To get chlorine to react with aluminium, I'll heat some foil in a stream of the gas. The white fumes are aluminium trichloride. With bromine, I just drop aluminium foil into the liquid. There's a short delay, but normal service is soon resumed.
All right. So that kind of gives you an idea of the difference in reactivity for these different halogens in that family. So hopefully you saw that fluorine is pretty freaking reactive, just as I was mentioning before. It is very, very big electronegativity, very, very big ionization energy. It is a bully. It's straight up the smallest kid on the playground, but the biggest bully. It's gonna come up and like sucker punch you in the back, right? It's a shorty little tiny kid, but it's like it packs a mean punch. So fluorine is really aggressive in this sense. It's very reactive. Whereas if you go down the halogen family, what you see is that the reactivity becomes less and less. Notice it took a lot more for the chlorine to react than it did the fluorine in that video. So as you go down the halogen group, it becomes less reactive. As you go up, it becomes more reactive. How about the other side of the periodic table? If we're looking at the left side then, and we're thinking about our alkaline earth metals, which one is going to be more reactive? Will they share the same trend as the halogens on the right side, or will it be opposite? Or maybe there's no difference. Let's find out. Again, thank you to whoever made this video, posted it originally. The link is in the description below for both of these videos. They are not my content, but greatly appreciated as somebody who does not have access to these materials for those who did take the time to post these videos. So hopefully you saw a vigorous reaction with the barium in whatever it's mixed in, right? They didn't say what it was mixed in or anything like that. That's inconsequential at this point. What we see is that magnesium, calcium, and strontium and barium are all in that same alkaline earth metal group or family. So then what we are interested in is which one is reacting most aggressively. That would obviously be the barium that you saw. And magnesium wasn't even bubbling. It didn't even bother bubbling once that I saw. So the reactivity of the alkaline earth metals as you go down that group becomes more reactive, which is the opposite of the trend we saw for the halogens, where if you went up the group, it became more reactive. So then what causes reactivity? This is kind of a throwback to one of my previous lessons when we were talking about shell models. Essentially, all of the atoms want to be the noble gases. They all want to be stable. They all want to be snobby. They all want to have full valence shells. They want to have that full outermost valence shell filled. In order to do that, they're going to steal or give away electrons depending on what's most useful for them. For example, lithium, remember, wanted to give away one and become positive in order to be stable, whereas oxygen wanted to gain two in order to be stable and have a full octet and be a -2 charge if it's gaining 2 electrons that are negatively charged. So oxygen would have to steal electrons to do this. Lithium would have to give away electrons to do this. So depending on which atom you are, depends on the strategy you take in order to gain noble gashood, if you will. So in order to do that, they are very reactive. If they are giving away aggressively, or if they are taking aggressively, like chlorine would, then they are more reactive. And this also plays into how big they are. It plays into their electronegativity, their ionization energy, and all the trends we've just talked about also influences their reactivity. So this concludes the lesson. Hopefully you should now be able to look at these words and define and explain each one of them and what they're used for. You should be able to look at a periodic table and tell me where the metals, nonmetals, and metalloids are. You should be able to tell me what going up and down is called, or going side to side is called. You should be able to tell me what charges each of these groups possess, and whether or not there are any charges in here. Remember, these are transition metals. That's one of the family names. You should also be able to explain what the names are for each family, for each group that we talked about. You should know the trend for ionization energy and for electronegativity, where it gets bigger or smaller, generally across the periodic table. So you want to think about going like this, right, across the periodic table. So if you go this way, you should be increasing in ionization energy and increasing in electronegativity. They share the same trend. And now for atomic size, if you go the other way, you get bigger. Up here would be smaller, down here would be bigger. You should also be able to explain Coulomb's law, how the force is dependent on the radius, the atomic radius, and the amount of charge to pull on that distance. And reactivity. Reactivity, if we're looking at the alkaline earth side, so over here, we know that as we go down, it becomes more reactive. And on the halogen side, we know that as we go up, it becomes more reactive. That's the periodic table for you in a nutshell. Hope you loved science just a little bit ducking more.
No ducks, no glory.